Today we're going to see another interesting topic, and that is giving this physical system here, this electromechanical actuator. Can we obtain transfer functions automatically for any output that we want? That's objective number one. Objective number two is to understand how do we obtain those transfer functions. And in order to do that, we have to understand the relationship between the state space form and the transfer function. So my idea is, let's take the second point first, because it will help us understand the first. Okay, so first I think we're gonna have to put the state space form in general form of this uh, of the system, or any system for that matter. So how is that? We have that the state space form looks something like this. It says x dot is equal to matrix A times the vector of state variables plus the matrix B times the vector of inputs, right? It also says that the output vector is equal to the matrix C times the state space vector plus the matrix D times the input vector. Correct? Okay. So what do we want to do? We want to understand ourselves. Let's say that I have an objective, say. You can say, given this state space form, this is our, what we know as a state space form. Okay. Given this state space form, obtain the transfer function. In general, a transfer function is going to be an output, which is in this case, like y. These are obviously in the S domain. And the input would be this, right? So as a concept, the transfer function is the output in the S domain in relationship to the input. Yeah, like that. Very good. So what I would like to do is, let's apply the Laplace transform to the state space form. And we say, okay, so I'm going to put in here, apply Laplace transform to a steady state, the state space form. So what do we have? We have that S times x of s. Yeah, this is the vector applying the Laplace transform, is equal to A times the vector x of s plus the matrix B times the vector u of s. Right? All right. And let's apply the Laplace transform to the second equation. So y of s is going to be equal to the matrix C times x of s plus the matrix D times u of s. Very good. So because we want the output, really, I think that we need to somehow get rid of x of s. So my idea would be, if you if you use this equation and we find an expression for x sub s and substitute on the second one, let's see where we go. So do you see here, you have x sub s over here, you have it on there here. You could put this on the other side. So you could have that s times x sub s like this minus a times x sub s like this equals to b times u of s. Very good. We could write this x of s, if we want to take this as a factor outside of this multiplication, you say this is x of s times si, the identity matrix, minus a, like that, right? Because we took x of s out. So this vector multiplied by this matrix is equal to b. Do you understand why we have to put that I in there? Because you see this thing is a vector and this is a matrix. So multiply the vector s by the x of s by the matrix I, which is the diagonal matrix, then we can actually do what we just did. I think we have a little bit of an issue here on the way I wrote this. Let's just make sure this is right. First, we need to keep them in the order that it came. So to be able to do the sum, as I mentioned, we will have to do si minus a times x of s, like this. There you go. Now everything is okay. So to be able to find x of s, let's multiply both sides by the inverse. So we have s of a minus a times the inverse times si minus a matrix times x of s is equal to the inverse, which would be si minus a inverse, and then this multiplied by b times u of s, right? But do you remember what a matrix inverse times itself is? This is just the identity matrix, right? This is the identity matrix, which would be which multiplied by the vector is just a vector, right? So there we go. So this is the identity matrix, like this. Very good. So this means that x of s is equal to si minus a inverse multiplied by matrix b multiplied by the vector u. So now this thing we could go and plug into this equation right here. See? and then we'll see where we go from there. So I am going to say that y of s like this should be equal to the matrix C times the Si minus A inverse, this matrix Si minus A inverse times B times the vector U of S. So that is C times X of S, which I just wrote, then plus the matrix would be D times U of S. Yeah. So now you could actually say that the output Y of S is equal to this C times the inverse of Si minus A times B plus D. And then this multiplied by U of S. Yeah? So what am I getting with this whole thing? Isn't it true that from here we could just write that Y of S in relationship to the U of S is going to be the matrix C times Si minus A inverse times B plus D. So what does this mean? This has a major meaning for us. Let's just go over here. I'm just gonna put it in red framing here. This is, as you know, this is the transfer function. See, the transfer function is this is saying the transfer function is related to the matrices this way, to C plus C times Si minus A inverse times B plus D. But obviously the transfer function, this transfer function of S needs to be a vector. Yeah? So we can get several transfer functions as a result of this, because you can see that the transfer function is a function of the matrices. So that's how we demonstrate this relationship between the transfer functions and the state space form. Why are we doing this? The reason is that we want to obtain transfer functions automatically. Yeah. So you could say you could say the fundamental principle. Let's write it down here. The fundamental principle is going to be, if we know the state space form comma, we can find out any set of transfer functions relating the outputs, in this case y of s, to the inputs, in this case u of s, and that is based on this right there, right? So once we have established this principle, all we would have to do is to define what the outputs are, know the other matrices, and ChemG and MATLAB should do the rest. So I'll repeat. If we know the state space form, which ChemG can automatically find, then the only thing that is left to do to obtain the transfer functions is to define what the outputs are so that the matrix C and D can be defined. And if the matrices A, B, C, and D can be defined, then using this expression right here, we can obtain any transfer function on the system. That's the conclusion. So if we apply it to this example that we have on this, we have it on our handy here. We need to define what the outputs are. So this 11 in here is gonna is marking this resistor. For example, let's just do the velocity over here, which this is 12. So let's say that F12 are our outputs. So this is one output. And let's pick up another output. I think I would like another output also. We could pick one on the electrical side. You could pick the voltage on this the voltage on the inductor. How about that? So this would be like E sub 3. E sub 3 would be the output. So E sub 3 and F12 are our outputs. So let's just go ahead and enter this into the ChemG software. I'm going to be entering it in the same way as I have it in here. And so let's go over here to ChemG. And we'll move it over here. This is what is nice about with this new version. We can move them and we can just build our bond graph model here. So in here, I'll just do it exactly as it is on the left hand side. You have an SE, and then you have a 1, which is over here. And then you'll put the 1 in there. We have an R element up here on this, and then we have an I element over here. Yeah. And then we have, this is a GY element over here. And of course, it's got the 1 on the other side, right here. Yeah. And then we have an R element over there. And then we have an I element in number 7, I think it is, right? There we go. And now we have a 0 over here. Yeah. And then we have a C element over here, like that. Yeah. And then this is the 1, which is this. And then you have this R element over here. And then finally 12, I think we have the another I element over here. Right here, right? Very good. We did something. You know what I did? I didn't put an I element in there. I put a 1. So we're just gonna fix this. We needed to put this one in here. I expected that the causality just would flip, just like it did right now. But sorry, I put a 1 in there so it wouldn't work. Just to make it clear here, our output in this case is F12 and the other output is E sub 3. I am going to save this picture right here that we have so that we know exactly the bond graph that we entered, and we put in our notes over here. So we have defined what F12 and E sub 3 are the outputs. So in here I am going to go to MATLAB and Simulink, to the interface of MATLAB and Simulink. Let's just go and hope that everything works just fine in here. In this, okay. Okay, so CAMG generates these files. One of those is CAMG SYM. If you run this file right here, you would obtain the matrices A, B, C, D, and then you have this matrix here. Let's just I haven't entered any values or anything like that. So what it does is, first of all, it's telling me what the input vector is, of course, the C1. These are the state variables. This is the vector of state variables. It's telling me what the outputs are. Output variables. We haven't defined it yet. So just the A matrix, the B matrix, and of course the C matrix is to still be defined. So what we're going to do here is, so the point what I wanted to make is the A and B matrices that do not depend on the output have already been generated. But because we do need the we do need the we need to find the two outputs. One was E sub 3 and the other one was F sub 12, right? So E3, please find it. And it does. It finds this right there. And you say, this is my first output, number 1. Okay. And please initialize the first row of the C and the D matrix. And then you have F12, which is the other one. So this is 2, and then you will initialize this. In other words, you have to wake them up, because these are like inactive terms when they have the percentage sign, and we have defined both of them. So at this point, we can run this again, the CAMG SYM file, and then you'll See, now it's clear. Output number 2 is F12 and output number 1 is E sub 3. You have the A matrix, you have the B matrix, now you have the C, and then you have the D. Once you have these matrices, you should be able to find the characteristic equation, which is the denominator of the transfer function in symbolic form, and you will find also the transfer function. So the transfer function for both of these inputs. So for both of these outputs, see the transfer function m is this numerator, and then you have it. In this case, we have two transfer functions, right? Because we have two outputs and one input. And so the first transfer function is here, symbolically. Then the second transfer function is right here. But it might make more sense if we actually give some numbers to this transfer to the physical parameters. Yeah, they are right here, see? Simulink has by default the option of setting all the parameters to 1 to see what it does. I don't think that that's just for the sake of example. These are not realistic values for the system, but just for the illustrative purposes of showing you the mechanics on how it works. I'm just giving these numbers to the physical parameters, and once I do that, I can actually obtain the response in okay, there we go. So now you see the A matrix is numerical matrix now, so is the B, and so is the C, and so is the D. This is the characteristic polynomial. It's a little easier to see it now. And these are the two transfer functions. So just to make sure how they relate to each other, the computer is going to give you a transfer function. And well, of course, it already ran with the transfer functions several things. But you see here from input 1 to the output, see, from the input to the output 1. So to what was our output 1? It's telling you here what the output is. See, output 1 is E3. So this is the transfer function for E3. It's right here also in like a matrix vector. But and there is for the 2. What ChemG did at this point is took those transfer functions and gave us the step and input response for both of those, for both transfer functions. But also, this is a very efficient system because what it did also gave us the body plots and the root locus plots, which one body plot is over here, the root locus plot is here for the first output, and this would be the body plot and the root locus plot for the second one. Okay, so my point is that you can get the automated transfer functions just by giving it the output here, and in symbolic form or in numeric form obtain the transfer functions. If you put numbers, you can also do a step input, impulse response, and you can get the root locus and the body plots. But at this point, the main objective was to obtain the transfer functions. And I think I have shown you also where and how, what's the basics of obtaining those transfer functions. That the derivation of this principle that I have established of obtaining the transfer functions with the matrices is implemented into the CAMG software. Because you see, right here is the statement. If you compare the statement of our one node here, C times Si minus A times B plus D, that's exactly what you're seeing right here. You see, is saying the matrix of transfer functions HC times the inverse of Si minus A times B plus D, all matrices. And when you execute this, you are going to obtain the transfer functions in this form. And when you put the numbers, you will obtain them in this form, and of course do the response. So I have shown you from scratch what the principle is and how CAMG and MATLAB automatically implement this process to obtain any transfer function of any output on the bond graph model.